Okay, thank you. So I'm going to tell you about transparent encryption of user data of a project we are working on in Lausanne. The project is 2u.ch. It's a platform that allows you to put information about what you want to do, well, what others need to do after you die. So like if you want to be cremated or buried, if you have any specific wishes after your death, choosing the color of your coffin, flowers, stuff like that. So it works like this. You register on the website, then you put your information. As I said before, your cremation wishes, the funeral music, stuff like that. And then you designate trustees that will have access to this data. Of course, this data can be quite sensitive because you can put like your social media accounts. And we don't want anyone who can hack the system to access this data. So it must be secure. So a client registers on the website, then enters some sensitive data, and then shares it with designated trustees. Of course, we don't want to have an attacker coming in and stealing the data. So let's see how it works. So this is a classical schema in which you have the client who sends data to the website. As you can see, we already use HTTPS. So an attacker cannot get the traffic that is exchanged between the client and the website. But on the other side, we have the sensitive data, which is stored in the database and on the file system. And this, by default, could be accessed by an attacker that could get, for example, a database dump or a file system dump. Before going any further, I need you to have some basic knowledge about cryptography. So I will just explain you two basic concepts, which are, the first one is symmetric cryptography. In symmetric encryption, you have a shared secret, which is called a symmetric key. And both parties need to know about this shared secret beforehand. So they need to agree on it first. So let's say Alice and Bob have met and they said, okay, the shared secret will be 1, 2, 3, 4. Then Alice can take some cleartext data and use this key to encrypt it. And then she will transfer the encrypted data to Bob. And here, an attacker couldn't decrypt the file without having this shared key. So Bob would be the only one, or any other person knowing the shared secret would be able to decrypt this data. That's why it's called symmetric encryption decryption. That's because it's the same key that is used for both encryption and decryption. The other type of encryption decryption is asymmetric. In this case, every person has two keys, one public key and one private key. The public key can be seen like an open lock that you would then use to encrypt the data you want. And then you use the private key to decrypt the data that was encrypted with the public key. So in this case, Alice will encrypt her data using Bob's public key. Then she would transfer it to Bob. In this case, an attacker couldn't decrypt it because the attacker would need to have access to the private key. And Bob would use his private key to decrypt the data. So back to our problem. So a client needs to be able to share data with more than one user. In this case, you can see Alice sharing data with, let's say, Barbara and Bob. And they both have a public key, which is the lock icon here. So we could use the public key to encrypt the data for each one of these users, but then we would end up with two versions of the encrypted data. And then for every user you want to share some data with, you would get a new encrypted version of your initial data. And it can be problematic if you start encrypting files. Let's say you have 10 megabytes files and you need to encrypt it for 10 people, then you have 100 megabytes because you duplicate it every time you want to share it with another person. So that's the solution we came up with. Each client registered on the platform gets a symmetric key generated. And then this symmetric key is encrypted for every trustee of this person. And then this key is used to encrypt data. So when Alice wants to add some data to the platform, she uses her symmetric key to encrypt it. And then the trustee, to be able to read this data, will first decrypt the symmetric key with her private key, giving the exact same symmetric key as Alice's used to encrypt the data. And then she would be able to use it to decrypt the encrypted contents. So a summary of what we have done now. When a user registers on the website, we generate a public key and a private key. If the user is a client, which means the person will enter sensitive data in the website, then we generate a symmetric key. And this symmetric key is encrypted with the client's public key. Of course, the clear text symmetric key is not stored, because otherwise anyone who could get access to the database would be able to decrypt everything. And when Alice adds Bob as a trustee, then we decrypt her symmetric key using her private key, and then re-encrypt it using Bob's public key. So each client has one public and private key. These keys are only used to encrypt and decrypt the symmetric key. And each client also has one symmetric key that is used to encrypt and decrypt the data. And trustees have one public key, one private key, which is also used to encrypt and decrypt the symmetric key. And they have one encrypted symmetric key for each one of the clients. And now you can see that Windows doesn't like emojis. But what about the private keys? Because as I said before, if we have a clear text key in the database, then someone that gets the database contents would be able to decrypt everything from the database. So it's not an exception for the private keys. If we store the private keys in clear text in the database, anyone who would get a database would be able to use these private keys to decrypt the symmetric keys and then use the symmetric keys to decrypt the content. So the secret here is that private keys are encrypted with the user password. But the problem is we only have access to the user password when the user logs in. This is the only moment we have it. It's when the user submits the login form, then we get the clear text user password. So let's see what happens when a user logs in. When a user logs in, she uses her browser to send the login form. Here you can see she sends the login and the password. And we have on the server the symmetric key and the private key, which are encrypted. So the first step is to decrypt the private key using the user password. Now we have the clear text private key. We generate a session secret. You can see here it's very secret. Well, actually, it's the key, very secret. And we will re-encrypt the private key using this secret. This private key will be stored in the session. And then we will send the session secret to the client as a cookie. Then it will allow us, every time a client gets a page from the website, the session secret will be sent along as a cookie, and we'll be able to use it to decrypt the re-encrypted private key, the yellow one on the slide. So let's see what happens when the client needs to actually encrypt data. Now the client is logged in. They have a session ID, which is like a standard that you always have. If you have PHP website, Django website, anything, when you log in, you have a session with a session ID in a cookie, and you have the session secret, which is the very secret string. So the client here sends some data to encrypt to the server. The first step will be to decrypt the session private key with the session secret to get the private key. Then we can use this private key to decrypt the symmetric key. And finally, we can use this symmetric key to encrypt the data. And the decryption process is exactly the same. If I come back to this slide, if a trustee logs in, they also have a session secret and a session ID. They also decrypt the session private key with the session secret. Then they decrypt the symmetric key. And then they can decrypt some encrypted data. So what about risks? Let's get back to the drawing of the big picture. So before, we only had the communication between the client and the server that was secured. Now we also have the database and the file system contents that are secure. So an attacker that gets access to either the database or the file system won't be able to decrypt anything. So both the database and the file system are safe. But if an attacker can break into the server, only the active sessions are affected. That's because the only way to decrypt the symmetric keys is by using the private keys, which are encrypted with the session secret. So the attacker would need to sniff the traffic between the client and the website to get this session secret. So even if you put some sensitive data on the website, and then you don't use your data for like 1 year, and during this time an attacker is able to get into the server, then your data would still be safe. So this solution was created for a first version of the product for the MVP. So it's not perfect. It's not perfectly secure. The right way to do it, I think, would be to encrypt data client-side. We did it server-side because it was easier, especially for encrypting files, because we also need to display inline images on the website. I'm not sure how you could do that in JavaScript. We have another problem about password recovery. So since the user password is used to encrypt the private key, then if the user loses the password, they won't be able to decrypt the symmetric key, so they won't be able to access their data. The solution we use is to create a super trustee account that is automatically added as a trustee when you register on the website. So then if a client loses their password, then we can generate a new private and public key pair and let them encrypt it and still use the same symmetric key we had before, because as a super trustee, we have access to all the symmetric keys. So it can be a weak point in the architecture, but that's the only idea we had. And finally, the code is not yet audited. I think it would be nice to have a security audit of the code. I'm quite confident about the approach we had, but security is very hard, and it's very easy to mess up things because of all the attack vectors you have. So that's all I had. I'm sorry I didn't show any code because there's quite a lot of code and little time to show it. But if you have any questions or if you want to discuss more about this, you can join a security guild. I would be very happy to talk about it a bit more. Thank you.
We have a question from Firu.
Yes.
So everything is encrypted using asynchronous encryption and all, but in the end, it's all down to the user's password. So if the user not loses, but gives his password somewhere, everything is broken, right?
Yeah, sure. I think in the end, the user is always the weak point. You can see the social engineering stuff. So if, we should at least, I think, enforce some password complexity. The only thing we do right now is to enforce a minimum password length of 6 characters, I think. But we should really improve this and maybe try to give some information to users about what are the best practices to keep a password safe.
Thank you.
Any other question?
Yes, I have a question or a comment. So as you know, by coincidence, we effectively have implemented the same thing, only in PHP. We have some differences. So the first thing, we use two-factor authentication. So at least if the user hands away their password, they also need to hand over their phone. The other thing is, so the way that we deal with the private key is a little bit different. So we use Okta for the two-factor authentication, and we actually store the private key at Okta, which means that the private key at Okta is actually kind of plain text for Okta, but the application has no way to get to that private key unless it has a valid token from Okta for that specific user, and it can then only read the private key of that specific user to decrypt. This has also the nice side effect that password recovery does not require sort of that super user account on the same server, but instead they can use the Okta password recovery and then to immediately get access to their old private key again. But it does mean, of course, that the super users that have access to the Okta management console, they also have access to all the private keys in plain text. So it's not necessarily more secure in the sense of like an inside job, but it is, I think, more secure in the sense that a hacker would also need to get access or control over the Okta service to get access. Whereas in the case where, you know, this super trusted user that can do password resets, if they get compromised, then like if the server is compromised and then they try to reset a user, and during that time the hacker can steal that password, yeah, they can get all the access. So I think it's slightly more secure with this Okta setup, but of course it comes with quite a lot more effort in setup and running, and of course Okta is not for free.
Yeah, sure. Thank you for the information. I think the most secure way of doing this would be to disable password recovery completely. I mean, I think that's how some password managers do it, I think, because then you are sure that there are no other ways to get access to the data.
Adi is asking in Bern if you have an audit plan.
If we have another plan?
An audit plan.
Oh, an audit plan. Not really. So the project is made for the Mobilier, the insurance company, and they have some security people in the company, but they asked for a price indication for a security audit, and I think it was very expensive. So we are waiting on getting a budget approval for this, but I think they will do it internally if they do it. Does that answer your question?
Yeah, thank you.
Yeah. Any other question? Okay, so enjoy your lunch.
Yep.